Good afternoon, everyone. Welcome to the live session of Introduction to Machine Learning of NPTEL. So, I will like to take questions from you and answer. We have already got some questions on the Excel sheet. So, I will be taking up the technical questions from there. So, there is a question that more explanation on nonlinear separability is needed. So, let me explain what you mean by linearly separable. Good afternoon, everyone. Welcome to the live session of Introduction to Machine Learning of NPTEL. So, let us first understand what we mean by linearly separable. Suppose you have a machine learning problem where there are two classes and you have instances belonging to both the classes. And suppose the instances are described in terms of n features. So, the instances are points in n dimensional space. If you can have a line or a hyperplane in this space which separates the points belonging to both classes, then we say that the class is linearly separable. And if the two classes are linearly separable, we can use a linear hypothesis space. We can use a linear function for regression, or we can use logistic regression if we are doing a classification problem. However, it may so happen that in your instance space, the boundary that separates the positive and negative points, a linear boundary cannot be found. Then we say this is an example of non-linearly separable. So, this means we cannot use a linear function and we cannot use linear or logistic regression. In that case, we have to use a machine learning algorithm which uses more powerful hypothesis space. For example, you can go for higher degree polynomial as your hypothesis space. You can use decision trees, or you can use neural networks with hidden layers which are able to capture more complex hypothesis space. I hope it clarifies your doubt. The next question says that you want to know about SVM. I think you have to look at the lecture again to understand SVM, but let me very quickly explain what an SVM is. Let us take an example where you have a two-class classification problem and the two classes are linearly separable. That is, there exist certain lines for which the positive points are on one side of the line and the negative points are on the other side. Now, there can be many lines which separate the positive and negative examples. In a support vector machine, what we do is, for the training examples, we find that linear function so that if you use the function as the decision boundary, the margin is the widest. That is, the distance of the closest positive point from the line and the distance of the closest negative point of the line, they are equal, and this is as large as possible. So, this is what SVM does. It finds a linear separator so that the margin from the closest points on other side is the largest. So, this is the simple linear SVM. There are some other variations of SVM that we have discussed. Firstly, for instances which are not linearly separable, one can define kernel functions so that if you transform the features to the kernel space, in the new space, the instances may become more linearly separable. This is called kernel support vector machine. Okay. So, in the original space, the points are not linearly separable, but when you give a transformation and go to a new space, it may so happen that the points are linearly separable or close to linearly separable. They are called kernel SVM. Another variation of this is when there is some noise in the data. So, even though the data points are mostly linearly separable, there is some noise in the boundary, so that you cannot really cleanly separate the positive and the negative points. In those cases, we use a relaxed version of the SVM, where we allow points to lie, some points, a few points to lie on the wrong side. And in that case, we define the objective function as a sum of, one is you want to make the margin largest. Secondly, you want to make the the points which lie on the other side, you want to make the error with respect to those points small. So, based on this, you can define an objective function, so that you can handle cases where the points are not quite linearly separable. This is the basic idea of support vector machine. I request you to go through the lecture again, so that you can try to understand more of this. The next question, so you have written that is the number of hidden layers proportional to the number of features. Now, when you have a problem and you want to solve it using a neural network, you have to design the architecture of the neural network, which means the number of layers you wish to use and the number of units in each layer. If the problem is complex, it will require, in order to represent the data, you will require larger number of nodes in the hidden layer. Also, if the problem is complex, you might want to represent it using a deeper neural network, that is larger number of layers. So, the depth and width of an appropriate neural network depends not always on the size of the input, rather than on the complexity of the classification and regression problem. The number of hidden nodes, every network that you design has a capacity, and the capacity depends on the number of layers and the number of hidden nodes in each layer. There is no formula, no easy formula to decide what should be the capacity, what should be the number of hidden nodes, what should be the depth. However, if the problem is complex, requires a great deal of nonlinearity or complex function to represent, you will require to represent it by a larger number of units in the hidden layer, which somewhat corresponds to how much the hidden layer can represent. Right? Every information which is required for to be extracted from the input, which will help you to get the output, must be represented in each layer of the neural network, and therefore, the number of hidden layers will be large when the function is complex. There is a question, PCA dimension reduction and kernel tricks are opposite. One reduces the dimension, the later increases the dimension. So, actually this is not quite the same. PCA and other methods of dimensional reduction, their objective is to have a compact representation of the input, and a PCA is independent of the output class. A PCA is defined on the input, only on the xi's, it does not use the yi. PCA is a means of compactly representing the input in a smaller number of dimensions, such that these dimensions are orthogonal and it captures maximum variance of the input data, and such that once you project the input to the PCA dimensions, the reconstruction loss of the input is maximum. This is the objective of PCA. The objective of PCA is to take some input and to represent it in a lower number of dimensions with minimum loss. On the other hand, The kernel trick is something different. Even though certain kernels take you from a lower dimension to higher dimension, because it is more likely that the points are separable in higher dimension, the analogy to PCA is not there. The objective of the kernel is to find a feature space where the instances are linearly separable. So, given a problem, it is not clear what kernel will be applicable for the problem. So, you have to find a kernel if such kernels exist, so that they can separate the positive and negative points. So, the kernel function depends on the classification problem that you are trying to solve. The PCA is independent of the classification or the machine learning problem. It deals with representation. Kernel deals with representation in a space where the two classes can be separated. So, they are very different. The next question is, what is the use of cross validation, accuracy and precision? So, when you use a machine learning problem, when you use a machine learning algorithm and you apply it, you have to know how good the algorithm is, so that based on that you can decide how to tune this algorithm or whether to use a different algorithm. And in order to evaluate how the machine learning algorithm is performing, you want to measure it. In order to measure, you have to check it with a new set of examples. So, you have a training set on which you train your algorithm, and then you must use a different set on which you will test the algorithm. So, training and test set must be completely separate. But in order to do the training during your development process, you will need to tune the parameters in order to decide what parameters to use, how many hidden nodes to use, what level of decision tree to use, whether to use linear classifiers or decision tree. So, these decisions you have to take based on the training set. Now, the training set can, your algorithm may overfit the data. So, you want to know how well the algorithm is performing. So, you divide the training set into a part which you use for actual training and a part that you use for validation. The validation set is used for parameter tuning and for algorithm selection by your algorithm, and based on this you develop your algorithm. And then this developed algorithm can be tested on a completely disjoint testing set. So, this is the use of a validation set. Now, cross validation is used when your training set is small. So, if you classify it into training and validation, the training set becomes too small and it is difficult to train. So, we use cross validation where we divide the training set into k subsets and we run k experiments. In each experiment, we set aside one of the sets for validation and the rest of the sets for training, and we run k instances of this problem and find the average accuracy. Next question, based on a given data set, how can we decide which technique is best to get optimum result? Now, this is a non-trivial problem. This comes with experience. There is no mechanical formula to tell you that given on a data set which technique you should use. You should get an idea about which algorithms use simpler hypothesis spaces, which algorithms can handle complex functions, and based on how difficult your problem is, you can decide what algorithm to use. There is no formula. Based on the complexity of the problem and the nature of the problem, the type of input variables, that is whether they are numerical or nominal, and type of the output variable, you have to take a decision on which algorithm to use, and you may have to use multiple algorithms to find out which one works, or for the same algorithm you have to tune the hyperparameters so that it is suited for the same problem. There is a question, please elaborate pack learning task. So, I just mentioned pack learning briefly. This is a theoretical foundation of machine learning. This is called probabilistically approximately correct learning. The objective in pack learning is to, you want to have a learning algorithm which can learn a function with high confidence it is approximately correct. That is, the error is bounded. With high confidence the error is bounded. So you have to find such an algorithm. And often in pack learning we try to have a framework, and for this framework we try to find out how many samples are required. Given a hypothesis space, how many samples are required so that that algorithm is pack learnable. There are questions at the YouTube channel. Okay. I will just take questions from the YouTube channel. So there is a question how decision tree deals with continuous features. Now suppose you have a feature, let us say height, which has continuous value. Now you have to find a range at which to divide. Suppose the height ranges from 4 feet to 7 feet, and you have to find a k such that less than k will be on the left side and greater than equal to k will be on the right side. And you will have to choose the value of k, that is the threshold for the continuous variable, for which, for example, if you are using entropy as your function, you have to choose that value of the threshold for which the gain is maximum. Okay. So, for continuous valued function, you have to identify a threshold based on which you divide the node into two classes. And for this you can use the training sets and the values of that variable, you can sort them and you can try to find out for which value the gain is the highest. How do we decide whether the model parameters are optimal? I think it's very difficult to answer this in general. For example, if you are using a neural network, there are so many model parameters. For example, there is this model topology, the number of layers, the number of nodes in each layer. Then there are parameters such as the learning gradient, the optimization function, the regularization parameters. So it is very difficult to tell how to choose it, but you can run a search on different types of parameters, and so that you can identify that value of parameters for which you get best validation accuracy. And with experience you can choose these parameters better in a faster manner. Sequential minimal optimization and constrained optimization. These are two optimization models, basic optimization models. Suppose you have a multiple variables which you want to optimize. In sequential minimal optimization, what you do is that suppose you have n variables, you keep n minus 1 variables fixed and you change the other variable, so that you find its optimum value. Then you keep that one fixed and choose one of the other variables to optimize. So this is how SMO works. It keeps all but one of the variables fixed and only changes one variable to get the optimization. And constrained optimization, there is no one algorithm. So you can define the optimization problem and the constraints, and there are various optimization methods that you can use for constrained optimization. Why put gamma equal to 1 in SVM? I am not sure what you mean by gamma. If in an SVM there is a version of SVM where you have the loss is composed of, one is the margin loss, the other is the loss based on the instances crossing over to the other side. So you can tune how much you look at, how much importance you give to each of them. So based on that you can choose the value of gamma. Okay, VC dimension is a concept from learning theory. So the VC dimension depends on the hypothesis space. So, given the hypothesis space, suppose you have a hypothesis space and you take 3 instances. Now, these 3 instances can be labeled in 8 possible ways for 2 classes. Suppose you have 2 classes plus and minus, you have 3 instances, any subset can be positive, rest of them can be negative. There are 8 ways of labeling these instances. We say that a hypothesis space is shattered by these instances if for all possible labelings of these instances there is an instance from there is a hypothesis which is consistent with that type of labeling of the instances. In that case, we say that the hypothesis space shatters those examples. VC dimension of the hypothesis space is the maximum number of points such that you can find one configuration of these instances, let us say the instance is k, you can find k instances which is shattered by the hypothesis space, and VC dimension is maximum such k. The VC dimension depends on the hypothesis space. The more complex the hypothesis space, higher will be the value of the VC dimension. So, it is a measure of the learnability, and the number of samples required for training in order to find a pack hypothesis depends on, one of the things that it depends on is the VC dimension of the hypothesis space. How to decide activation function in neural network? The older neural networks used activation functions like sigmoid and tanh. There were issues in using sigmoid and tanh when you have deep neural networks. In deep neural networks, these functions suffer from gradient diffusion or gradient explosion. Nowadays, people use as activation a simple function called ReLU or some variant of ReLU. Now, this ReLU activation function is very simple. It is max of 0 and x. The ReLU activation function is a function which does not suffer from these defects. And there are some variants of ReLU activation function which are popularly used when you have a deep neural network. When you have a shallow neural network, you can use a function such as sigmoid or tanh. This is at the internal layers. At the output layer, if you have a regression problem, you do not use any nonlinear activation, you just use a linear function. If you have a classification problem, 2-class classification problem, you use a sigmoid function at the output. If you have a multi-class classification problem, you use the softmax function. Next question, while finding geometric margin, we put gamma equal to 1. Why is this assumption? I think this is by definition. We have this functional margin and geometric margin, and we have explained the reason why there are these 2 different margins, because one of them is sensitive to the actual parameter values of the function. So, gamma equal to 1 is by definition we have gamma equal to 1. While applying CV equal to 10, there may be features with categories present in training, not in test. How to deal with that? CV means cross validation. There may be features with categories present in the training, not in the test. You see, in general, it is not just for cross validation. In machine learning is a generalization problem. It can always happen that whatever you encounter in the test instances was not present in the training instance, and in that case it is not possible to learn that feature. However, if we make a simple assumption that the training population and the test population are the same, then only we can deal with the generalization problem in machine learning. If you only see one type of training data, suppose you see only black and yellow tigers in your training data and your test data has only white tigers, there is no guarantee that your learning algorithm will succeed. But if you make the assumption that the training and test samples are randomly drawn from the same distribution, the number of new types of instances which are available in the test set may be restricted. Therefore, your overall accuracy can be high, even though you may not be able to classify the those instances or those features, those phenomena which were not seen in the training set, they may not work. So, this is true whether you use cross validation or not. In cross validation, the advantage is that it may be that for some of the splits you do not have a particular feature, but in other splits you have that feature. Because you are averaging, you can take advantage of that. But in general, if you have not seen something in training, you will not be able to, there is no guarantee that you will be able to handle this correctly. However, if most of the test instances are similar to the training instances, your algorithms will do well if you have learnt a proper function. What is the concept of bagging and boosting? Bagging and boosting are two types of ensemble methods. They work in different ways. In bagging, what you do is that you are given a training set, you generate different, so you run different instances of the machine learning algorithm. Each time you randomly select a sample of the available training examples randomly. So, suppose you have 100 training examples, you randomly select 50 training examples and run your algorithm once. For the second experiment, you again randomly select another 50 training examples. Now, these two sets may have something in common, but may have a lot of different these things. So, if you generate a random input sample from the same full training set for each of the experiments, it is likely that each experiment has a little bit different distribution of the training data and may give you different classifiers. And then you can combine these classifiers in ensemble learning. So, bagging depends on choosing a different subset of training instances at every trial. Boosting, on the other hand, keeps the set of training examples fixed, but it varies the importance that you put in the training example. To start with, in boosting, you consider that every training example is equally important. That is, you give each of them a weight factor of 1. After that, in experiment 1, you learn a classifier. Now, you evaluate this classifier on the same examples and you find out which examples the classifier is able to handle correctly and which examples you are making an error. Now, you will like to have the subsequent classifiers to do better for those instances where your first classifier has made mistake. So, what you do is you increase the weight of those examples which were misclassified, right? And proportionally decrease the weight of the examples which were correctly classified. So, after you have got the second trial, for the third trial again you repeat the same thing. You check which of them has not been wrongly classified by this classifier and you increase the weights, decrease the weights for the rest. So, with increasing number of iterations, you are giving more and more importance to those instances which were not correctly handled by the previous classifiers, and this is how boosting works, and you find an ensemble of these classifiers. So, these are two different approaches for ensemble learning. Bayes optimal classifier and Gibbs sampling. Now, a Bayes optimal classifier, as we have discussed in class, we want to find, if we want to find a classifier which finds the best classification. So, suppose we have two classes, plus and minus, and we have different classifiers. The Bayes optimal classifier is that classifier which will have the make the best classification among those classifiers, but finding the Bayes optimal classifier is computationally hard. Gibbs sampling is a method of since finding the Bayes optimal classifier is hard, Gibbs, because you have to check all possible classifiers and find out which classifier is giving you the best result, and it becomes intractable. Gibbs sampling is a randomized method of sampling from the different possible classifiers, and on the basis of this you select your classifier. So, Gibbs sampling is used to give an approximation, to find an approximation of the Bayes optimal classifier. The next question is how PCA deals with categorical variables. So, typically PCA is meant for numerical variables. For categorical variables, if you want to apply PCA, you have to convert it into numerical variables. Suppose you have 4 classes in a categorical variables, you can convert this into one hot vector, like you can represent it as 4 binary classifiers with values of 0 and 1, and then you can use PCA. But PCA usually works best with numerical variables. The next question is Bayesian optimization for hyperparameter tuning. There is no one answer for this. The optimization for hyperparameter tuning, it depends on what algorithm you are working at. In general, the hyperparameter tuning may not be a standard algorithm which will guarantee the most optimum hyperparameter tuning. So, this question is not very clear to me. The next question, why does overfitting happen? Now, you are trying to find a classifier based on your training set. Now, if you choose a hypothesis space which is complex, it is very likely that the hypothesis that you find tries to accommodate the training instance and gets a very small error on the training instance. Now, the training instance may be noisy. The training instance, the features, they may not be representative of all the information in the training instances, but because you have limited number of training examples and you are using a complex hypothesis space, you can get a very low error on the training instance, and in the process you may fit in the noise. Now, this hypothesis, when you apply on the test instances, it will not work well. This is when we say overfitting has occurred. So, if your hypothesis gets so tuned to the training instance that it fares much worse on the test example, this is due to overfitting. Overfitting can happen when the number of training instances is small, when the hypothesis space is complex, or when the number of features is large. There is a question, advantages of naive Bayes. Naive Bayes is a very simple algorithm which makes certain limiting assumptions. For example, it makes the assumption that the features are independent given the class. Now, based on this assumption, there is a very simple algorithm for doing the classification. And the advantage of naive Bayes is its simplicity. It's very easy to find the parameters, and in some cases it works well, but because it makes these simplistic assumptions, it does not work well in all cases. It works for simple problems. Application of Adaboost. Adaboost is a boosting algorithm. We just explained what a boosting algorithm is. It is an example of an ensemble algorithm. Ensemble algorithms, ensembling means doing a combination of multiple algorithms, and when you combine multiple classifiers, what happens is the error reduces. For example, the variance, the two major sources of error are bias and variance. So the variance reduces if you use an ensemble, because even if your algorithm is fitting the idiosyncrasies of the training data, because you have multiple classifiers, each one of them may not fit the same idiosyncrasies. So when you take a combination, the variance error reduces. So this is the advantage of Adaboost, or for that matter any ensembling algorithm. It reduces the variance error. How to decide layer in neural network? Well, as I said, this is a craft, or there is no formula to decide the layers in the neural network. Depending on the complexity of task and by trial and error, you have to decide the topology of the neural network. And it also depends on how many examples you have. If you have too few training examples, you should not go for a complex classifier. You should keep the number of layers, number of nodes, etc. small. However, if you want to accommodate complex function, you have to use a deeper neural network. The other thing that you can do is that you can use regularization so that you can use deeper neural network in all cases. The question is multi-layer neural network. So, this is a big topic. A multi-layer neural network is a network which has at least one hidden layer, one or more hidden layers. And in that layer, there is non-linearity. So, a neural network which has a non-linear hidden layer can express complex non-linear functions. And that is why we use multi-layer or deep neural networks. Now, when you have multi-layer neural network, so each neural unit has a weighted sum of the inputs followed by an activation function, which is non-linear. As we discussed, a non-linear activation function such as sigmoid or ReLU can be used. And a neural network with hidden layers and having sufficient number of nodes in the hidden layer is able to capture very complex functions. However, the challenge is, given some training set, how to learn the parameters or weights of the neural network. For this, we use the ubiquitous gradient descent algorithm, or rather its variant, the stochastic gradient descent algorithm, which work on mini batches. The details we have discussed in the lecture. So, first of all, multi-layer neural networks are used to represent nonlinear hypothesis spaces. And the deeper and wider the network, more is its capacity and more complex functions can be represented. The second aspect of a multi-layer neural network is how to train the network, that is, learn the parameters, and the weight parameters are learned by gradient descent. Next question, how to understand underfitting versus overfitting in test set. So, usually what you do is that you test your model on the training set and the held out test set. If there is overfitting, then the model will have very low error on the training set and much higher error on the test set. If there is underfitting, the error on the training set will also be very high. Both the training set and test set is high. This is underfitting. If the error on the training set is low, and the test set is high, it is overfitting. A random forest is an ensemble of decision trees created in a particular way. So, in a decision tree, if you remember how a decision tree algorithm works, you choose a variable at every stage. You choose a variable which you use at every, starting from the root, at every stage you choose a variable on which you branch. You choose the branching variable. Now, if you want to use an ensemble of decision trees, you want all the decision trees trained on the same data set to be very different. In order to force the decision trees to be different, you have to use some randomization methods. That is, the variable that you choose for the branching, you choose it by a random process, so that every time you run the algorithm, you might get different results, different root nodes. So, you introduce some randomization in the variable branching factor for the decision tree algorithm, and then you develop a number of decision trees from the same training data set, and you use an ensemble of them. That is called a random forest. Okay, so are there any other questions? You can post them on the YouTube if there are more questions remaining. I think there is one question which says, given the hype about neural network, can there be applications where neural network may not perform as well as some other classification algorithm like SVM and logistic regression? As I said, there is no need about hype. The learning algorithm which is required depends on the capacity, the task complexity. If the task is simple, you should use simple methods like SVM, logistic regression. These are all linear methods. So, you can use SVMs when the decision surface is linear or near linear, or if you can find a kernel which is able to map it to a space where it is linear. However, if you have more complex tasks, then only you should go for neural networks. So, the idea is to be aware of different machine learning algorithms and their properties, and use those algorithms or combinations which are most suited for the given task. Sample complexity lower bound with VC, I think the some formula is worked out in the lectures. Again, pack learning, we have very briefly talked about pack learning to make you aware of how the number of examples, the complexity of the hypothesis space, etc. are related. You please look at the lectures for doing this. There is a question, do you really use naive Bayes in practical application? Again it depends. If it is a simple problem, for example, text classification, naive Bayes gives a reasonably good result. SVM gives a slightly better result, but SVM is more complex. So, you should use the appropriate tools. In machine learning, the different algorithms are different tools in your hand, and the tool you should use which is appropriate for the given problem. So, there are two aspects, how complex the task is and how much resources are required. Resources in terms of space resources and computation resources. There are a lot of questions about research trends, other frameworks. This, let me just tell you, I cannot answer all the questions. Let me just tell you, this is a very introductory machine learning course. The objective is to familiarize you to the basic techniques of machine learning, especially the standard simple techniques of machine learning, and have a very brief introduction to neural networks. If you want to delve deeper into machine learning, first of all, you have to read other books or other deeper courses. Secondly, to do machine learning, it is very important to actually do hands-on work on hands-on examples. So, if you want to apply machine learning, it is a good idea to participate in several spaces where you can actually code and use machine learning algorithms. There are various forum through which you can get your hand on machine learning data sets and code, and different platforms of machine learning libraries like sklearn, Theano, Keras and so on, and you can experiment with them. Someone has asked about recurrent neural network. Again, in this course we have not gone into the depth of recurrent neural network. You should do a course on deep learning. A recurrent neural network is a neural network which can handle sequential data. So, in a recurrent neural network, you have input at different time steps, x1, x2, x3, etc. xi is the input at the ith time step. So, you have input at different time steps and they have the output. The output can be one output or multiple output. And recurrent neural network is a way to represent these sequential process by a network where the weights are shared across time steps. A recurrent neural network can be converted, can be looked upon as a normal multilayer neural network if you unfold the network, unfold the times into different layers. So, it will give you a very deep multilayer neural network. You can look upon it like that and use the similar back propagation method with time truncation in order to train that method. But details of this have not been taught in this course. You should take a course or read a book on deep learning to get more familiar with RNN, CNN and other newer types of neural networks. The final examination will be based on the lectures in this course and whatever you can infer from the concepts that have been taught in this course. And there will be multiple choice questions, somewhat similar to the weekly assignments that you have given, of the same format. Okay, so there is a question, difference between supervised and unsupervised learning. Supervised learning is where you have examples xi, yi, where x is the input, y is the output, and you try to find a function which maps from x to y. Unsupervised machine learning, you only have x's, there is no defined output. However, unsupervised learning means you have unlabeled data and you can do different things with unlabeled data. For example, in this class we covered different clustering algorithms. Clustering algorithms are means to group unlabeled data, and we have looked at k-means clustering, then AHC and a few other clustering methods. I am sorry, I will not be talking about any career opportunities in machine learning. I do not take interns. So, there are a lot of forums through which you can explore these opportunities. Okay, so any other questions? You are asking about mathematics book for machine learning. I think I cannot recommend any particular book right at the moment, but for machine learning it is very important to have a good understanding of probability, statistics and linear algebra. Some of the machine learning books themselves will contain a little bit about these topics, but it is better to learn these subjects separately: probability, statistics and linear algebra. And if you want to get into algorithm development, then optimization methods. These are the fundamental mathematics that you will require to work with machine learning. When should you use classification over regression? Whether you use classification regression, that is defined by the task. If the task there is a single numerical output, you use regression. If the output is numerical, use regression. If the output is nominal, a number of classes, you use classification. Like if you want to predict the price of a house or predict the amount a user will spend on an e-commerce website, that is a regression problem. A classification problem is given some instances to group them into different classes, that is called a classification problem. How much time it will take for learning machine learning in full length, it's up to you. There is a lot to be learnt in this topic. It depends on to what depth, how much you want to learn. I have been into machine learning for quite some time and I am still learning every day. So, there is no end to learning, new things are happening and you have to keep track of what is happening. Linear regression is used for regression problems, logistic regression is used for classification problem. What a logistic regression does is that you have a linear classifier followed by a sigmoid function, so that you can decide which of them will belong to one class, which of them is the other class. So, logistic regression is a linear function for classification problem. So, which is done by a linear function followed by a logistic function, by a sigmoid function. And linear regression is just a linear function which can give you y from x. Is there any way beyond gradient descent for learning? Gradient descent is the standard way of learning for neural network training. There are other ways which are more complex, which are not so commonly used, such as using the Hessian and other things, but they are not so common. The C parameter in SVM controls how much you want to make the margin wider or you want to make the misclassification smaller. How is a decision tree pruned? There are several methods. One of the methods is first to develop a complete decision tree, then you try to identify subtrees such that after removing the subtrees, your improvement on the test set will increase most. That is one method of post pruning a decision tree. Develop a big complete decision tree and then identify subtrees to remove such that it improves the accuracy on the test set, and among all subtrees it gives you the best. Then there are pre-pruning methods. While growing the decision tree itself, you do not grow the decision tree fully, you decide when to stop. I think we have to stop now. There are someone is talking about the SMOT algorithm. Can you please suggest good repositories through which you can find research papers? First of all, you can look at Google Scholar, which contains a repository of all relevant computer science papers. For machine learning, now there are various blogs and other forums which write about the new machine learning algorithms which are coming up. There are some LinkedIn groups, Facebook groups, blogs which discuss about it, but going through Google Scholar gives you a complete repository. Also, if you follow the major conferences in machine learning such as NIPS or NeurIPS, then ICML and ICLR and such conferences, you can look at the papers published each year and then you can see what are the new things which are happening in this domain. Is it recommended to keep C as high as possible? As I mentioned, C is a trainable parameter. You keep it small or large depending on what you require. You can do a simple exercise by changing C and find out how it affects the classifier. Suggest me a book for ML. There are several books for ML. I am not familiar with all the books. The classic book, there was a book by Mitchell, which is a very nice book to read. However, it does not contain all the concepts. Now there are various other books, like this book by Bishop on pattern recognition and machine learning. There is a book by Kevin Murphy, and various other books are there, and they are coming out. So there is a book on deep learning called the Deep Learning Book. If you are interested in neural networks, you can follow that book. So unfortunately, we have to stop now because it's the end of the session. So thank you very much for joining us in the session, and thank you on behalf of the TAs for the course. I request them to come forward because they have been answering your queries on the forum. So this is Ishani Chakraborty, Ishani Mondal, and this is Shukarna Purakayasto. So they have been the TAs for this course, and on behalf of myself and all the TAs, I thank you for joining this session. I thank you for participating in the course, and we wish you all the best for your exam. If you have further questions, you can post them in the forum and we'll see what we can respond. Thank you very much.